This is Lecture 1 for Module 3 in the book Problem-Solving Guide for Electromagnetism and Optics. The concept of voltage, trying to understand what the heck voltage is. It's misunderstood by many. As Electric Fence Company writes, 10,000 volts running through it. Voltage doesn't run through anything. Newscasters often say 10,000 volts of electricity. I don't know what that means. 10,000 volts of electricity. There's some potential difference of 10,000 volts, but was there a current there? Is it dangerous? I don't know. I don't know what that means. We're trying to understand the concept of voltage, develop a fundamental understanding of what voltage is. So let's think about a battery, because that's where you hear volts a lot, from a battery. Battery has two terminals, positive and negative. The voltage of the battery is the potential difference between the two terminals. So a car battery, 12 volts. One terminal is positive, the other terminal is negative. The negative terminal, the electrons are jacked up. They're too close together. They want to get off. They're pushing on each other. The positive side needs electrons. It's missing electrons. It wants electrons. It will grab electrons from any place it can. And one way to do this, not recommended, is to put a wire across here. Man, those electrons are going to run over to the positive side. There will be sparks and heat and a lot of energy. Don't try this at home. What the heck is potential difference? What does that mean? I didn't explain anything. Perhaps the best way to understand what a volt is to think about it as a joule per coulomb. It's like trying to understand what speed is by considering the unit knots. So many knots. Meters per second is easy to understand as a speed because you can think about 1 meter, 1 second. I can picture what that is. So let's not use volts. Let's use joules per coulomb instead. So a voltage difference is the amount of energy per charge a charge gains by falling through the field. So if I have a 1 nanocoulomb charge falling through a voltage difference of 12 volts, it's going downhill. It's going to gain, the change of kinetic energy is the electric charge times the voltage, which is the joules per coulomb. The energy per charge times the charge will give you the change in energy. So if it's 1 nanocoulomb and the voltage is 12 joules per coulomb, the energy change will be 12 nanojoules. So the way the voltage manifests itself, it's the energy per charge. The change in voltage is the change in energy per unit charge. To try to develop this fundamental understanding, we can consider gravitational voltage. Nobody talks about gravitational voltage, and there's a reason for it. Here's the gravitational voltage. It's the GH. G delta H is the change in the gravitational voltage. So when a mass falls through a gravitational voltage, a gravitational potential difference of G delta H, its change in kinetic energy is M, the gravitational charge, times the change in voltage. This is the kilograms. This is joules per kilogram. That gives you the joules. And the gravitational voltage is just G delta H. So if you put it all together, you get mg delta H, but you know what this is. This is the gravitational potential energy. That's the change in kinetic energy. You know this equation already. We're just applying it as gravitational voltage with the hope that it helps you understand electrical voltage. So we can complete the analogy by putting the field in there. The electrical voltage is E delta D. This is the direction in the field. That's the electrical field. The gravitational voltage is the gravitational field, little g, times the distance moved in the direction of the gravitational field. So you can get the electric field from the change in voltage. So, do you understand this yet? No. We have a long way to go. You can nod your head, but I'm guessing you do not have a fundamental understanding of voltage. So let's consider two metal plates that are connected across a 12-volt battery. When we close the switch, what's going to happen? Well, the positive side. This positive side would love to have some electrons. It's missing electrons. It wants to grab electrons. There's electrons over here on the other terminal, the negative terminal, and these electrons are all jacked up, pushing on each other. We need some space. We got to get out of here. These electrons are repelling each other. The positive side would love to have some electrons. What do you think is going to happen when you close the switch and you connect it to these two metal plates? Positive side is going to pull a bunch of electrons off of this metal plate. Metal plate's a conductor, has a bunch of electrons on it. Electrons can move. They will get attracted to the positive side. The electrons over here on the negative terminal will say, thank God we can go. They're going to come out all over here. They're going to spread out. They're going to try to get as far away from each other as possible. And you would think that it would relieve the stress here, but it doesn't, because the battery is a source of constant potential. There's a chemical reaction that goes on here, and it makes the electrons, again, as jacked up as they were before. So now they're very close together on the plate. The battery pulls electrons from this plate and pushes them on that plate. So now everybody's back at 12 volts. This plate would love to have some electrons. This plate has way too many electrons. That's what a battery does. That's what potential difference means. So when connected, the battery pulls electrons from the top plate until the potential difference across the plates is 12 volts. Separation of charge produces a field between the plates. There it is. The top is positive. The bottom is negative. The field lines go this way. A positive charge that released from the top plate, if I take a positive charge and stick it here, it's going to accelerate. It's going to go down the field lines. And it's going to gain 12 joules of energy for every coulomb of charge it carries. We can calculate the energy it gets because it's falling through 12 volts. It's Q delta V. Further, we can determine the electric field between the plates if we know the distance between them, because we have this equation right here. If the plates are 1 centimeter apart, we know that the voltage difference is E times D. We can solve this equation for the electric field. If we know the voltage distance, the voltage and the distance, the separation, we can calculate the field. So solving for the field, we get this. If there's 12 volts between the plates and the plates are 1 centimeter apart, the field is 12 volts per centimeter. If it's 12 volts every centimeter, it's 1200 volts in a meter. Wait a minute. I thought the units of electric field were newtons per coulomb. We talked about that. Newtons per coulomb. Now all of a sudden we got volts per meter. How is a volt per meter related to a newton per coulomb? Well, a volt is a joule per coulomb, and a joule is a newton meter. So we can start with volts per meter. We can take the volt and make it a joule per coulomb. We can take the joule and make it a newton meter, and the meters cancel, and we get newtons per coulomb. So the units are the same. If I ask for electric field and you say newtons per coulomb or volts per meter, those units are identical. You can give it in any units you want. We do the same thing with lowercase g, the gravitational field of the Earth. If we give it in acceleration terms, we drop something and we measure the acceleration. The gravitational field of the Earth, we say the acceleration due to gravity, 9.81 meters per second squared. If we're talking about the force, we express it as newtons per coulomb. The gravitational field of the Earth is 9.81 newtons per kilogram. Newtons per kilogram. It's a gravitational field. If it was an electric field, it would be newtons per coulomb. If you go to Jupiter, little g is 25 newtons per kilogram. So if I bring a 1 kilogram mass to Jupiter, the gravitational field of Jupiter would pull on it with 25 newtons. If I go to the moon, it's about 1.7 newtons per kilogram. A 1 kilogram mass on the surface of the moon will experience a gravitational force of 1.7 newtons. Now, we don't use gravitational voltage because there's no such thing as a gravitational battery. It doesn't make any sense. You can't imagine I drop something and it's going to get 12 joules per kilogram. There's some kind of a gravitational battery that's going to produce a constant potential difference. We don't have that. There's only one type of gravitational charge, and we call that mass. There's two types of electric charge. So there's no such thing as a gravitational battery, so we don't use the concept of gravitational voltage. But it's useful when trying to understand electrical voltage. Electrical batteries do just this. They are sources of constant potential. They keep the potential difference constant, and it's interesting and educational. It'll help you understand the concept of voltage, to consider what happens when you move the plates closer together with the battery connected. So here's our plates, battery's connected, there's a field between the plates. Now I'm going to move the plates closer together. What do you think happens? What's the potential difference between the two plates now? It's 12 volts by definition. It has to be 12 volts. The battery is connected. The potential difference has to be 12 volts between those two plates. So if I drop a positive charge from the positive plate to the negative plate, it has to get the same kinetic energy, because that's what a volt is. It's joules per coulomb. If I drop a positive charge from the positive plate here and it falls to the negative plate, it's going to get a certain energy. Since the potential difference is 12 volts here, if I drop a positive charge from the positive plate to the negative plate, it's going to get the same potential energy difference, same kinetic energy difference, because 12 volts is joules per coulomb. How does it do that? How can it get the same kinetic energy change when the distance is smaller? Well, the field has to be stronger. It's got to be pushed harder. And that's exactly what happens. When you move the plates closer together, the battery sucks even more electrons off the top plate and jams them on the bottom plate. So the charge separation is increased, and the field looks like that. The acceleration of the positive charge is greater. It has to be if it's going to get to the same speed when it hits the negative plate. So the battery is a source of constant potential difference, which means when it goes from one to the other, the energy difference per charge is the same, because that's what a volt is. It's a joule per coulomb. So while we're talking about batteries, there's some other misconceptions that are worth clearing up. Voltage does not flow, and you probably should understand that by now, right? The voltage doesn't go anywhere. It's the charge. When you connect the plate, the battery to the plates, the charge moves. The voltage doesn't go from one flow. It's like saying height flows. Height flows. I don't think height flows. This point's higher than that point, but the height didn't flow up or flow down. The gravitational potential energy didn't flow up or flow down. The mass falls in the field. A battery is not a source of charge. It's a charge pump. The battery doesn't have any charge in it. It just moves charge from one side to the other. When you connect the device across the terminals, the battery puts a voltage of 12 volts across the device. And of course, it's easy to see why this is a misconception because of the terminology used. If you fill up your car with gasoline, you take some gasoline from the tank in the ground and you put it in your car. Now you have gasoline in your car. There's a transfer of mass. I get to plug in your electric car. It looks the same. There's a pipe there. I'm going to fill up my car with charge. just like you fill up your car with gasoline. I have a full charge. I filled up my battery. That's not what happens. The batteries in an electric car have the same net charge whether full or empty, and that net charge is 0. When an electric car is charging, there's no net flow of charge through the cable. There's charge going in, there's charge coming out. There's 2 ports. One is in and one is out. Same amount of charge goes in as comes out. Well, what the heck's happening then? If the same amount of charge is going in is going out, how is the battery getting charged? That's a great question. The electrons that are going into the car are jacked up. They're close together. They have a high potential relative to the electrons coming out. This high potential is used to charge the battery. If you have a lithium-ion battery, it pushes the lithium ion up a potential hill. There's a chemical reaction that goes on, and you're pushing the lithium ions to high potential. When you use your device, a phone, for example, a Tesla, the lithium ions flow downhill via a chemical reaction. And that's how you get energy out of the battery. When you got a whole bunch of your lithium ions are at the bottom of the hill, you say, man, all my ions are at the bottom of the hill. I got to push them back up again. You got to recharge your battery. So that's what a charger does. Power stations do this because humans use power during the day, don't use so much power at night. So during the night, they pump water up the hill. And then during the day, when they need power, they let the water come down the hill, turn the turbines, make electricity. There's one more concept we need to talk about that's useful when working with voltages and fields, and that's the concept of equipotential lines. Like it sounds, lines of equipotential are lines along which the potential does not change. Gravitational equipotential lines near the surface of the Earth are parallel to the ground. If you move parallel to the ground, your potential energy doesn't change because your height doesn't change. So here's the Earth. Here's some equipotential lines. If I move from here to here, I don't speed up via the gravitational field. If I go down the hill, I speed up. If I go up the hill, I slow down because of gravity. Electrical potential lines equipotential lines for electricity, for voltage, are very similar. So here's a charged plate. It's a negatively charged plate. Here's an equipotential line. If I take a positive charge and move it along this line, it's not going to speed up or slow down. If I have a positive charge and I shoot it up, it's going to slow down because it's pulled down by the plate. The force is down, just like here. The gravitational force is down. If I have a positive charge, the force is down. If I release it from up here, it's going to fall to the potential and it's going to accelerate. Moves along this line, these are equipotential lines. No change in kinetic energy. The potential is the same. We can put some numbers in. In a gravitational field at the Earth, these are 1 meter apart. 10 joules per kilogram. If I bring a kilogram mass up 1 meter, it gains 10 joules of energy. Up another meter, it gains another 10. Up another meter, it gains another 10. Here's some equipotential numbers for electricity. A joule per coulomb is a volt. 0 volts, 10 volts, 20 volts, 30 volts, 40 volts, 50 volts. Positive charges fall down the field, the equipotential lines. So positive charges get forced to lower potential. Negative charges go the other way. You have to be a little bit careful with electricity because there's 2 types of charges. Gravity, we're always going down. Gravity is always attractive. Okay, so a joule per coulomb is a volt. Hopefully that increases the understanding. A good way to think about voltage is always think about it as a joule per coulomb. If you want to measure the voltage between 2 points, A and B. You release a charge from A and allow it to fall to B. Then you measure its kinetic energy. And to get the voltage difference, you take the change of kinetic energy and you divide it by the magnitude of the charge, joules per coulomb. So if you understand this, and some newscaster says 10,000 volts of electricity, I don't know what that means. So, perhaps you're ready to begin to develop your problem-solving ability for problems involving electric potential. The best way to develop your problem-solving ability is to solve problems, not surprisingly. So let's do one together. This is problem 3.5 from the book. The equipotential lines in a field region are parallel and 5 centimeters apart as shown in the figure. What is the magnitude and direction of the electric field at point A? What is the electric field right here? Let's think about this. Let's forget about part B. We want to know the electric field at this point. How do we get the answer? You're actually at the crossroads here. We have a hard problem. We have to get the field there. There's two ways to think about this problem. One way is like a sheep. A sheep thinks, this is an ordeal I have to endure. This is an unpleasant duty to figure out this electric field. It's the price I have to pay to pass this course. Isn't there some equation I could plug it into? What am I supposed to do? Sheep want to avoid thinking. They want to remember something, plug something in, get some help. Somebody help me out here. I need help. I don't know what to do. A wolf also doesn't know what the electric field is at point A, but the wolf treats it as an opportunity to develop. The wolf doesn't think, what am I supposed to do? The wolf thinks, how can I figure this out? It's an intellectual challenge. I want to improve my understanding of the concept of voltage and electric field. Don't help me. I don't want help. I don't want a hint. Leave me alone. Let me think. And today's employees are looking for wolves. Wolves that say, give me the damn ball. Put me in, coach. I got this. Apple recently said, we don't hire anybody that needs a manager. Steve Jobs says, we don't hire smart people and tell them what to do. We hire smart people so they can tell us what to do. The goal of doing physics problems like this is not to be able to calculate electric fields. The goal is to develop problem-solving skills, mental strength, mental stamina, the ability to sit hard for a long time and try to figure something out. And that's what I recommend you do right now. Stare at this figure and say, what's the electric field? What does it mean? I don't understand this. How can I figure this out? Let me think hard. And after half an hour, if you still don't know what the electric field is at point A, watch this whole thing over again. Voltage is an extremely difficult concept to understand. It takes a while. It's a great investment, not because you understand voltage, but because you have the ability to think hard and figure something out for yourself. And this is a noble cause. Develop your talent. Okay, I'm going to give the answer to part A right now. So stop me. Stop the video. So what's the electric field right here? Well, the voltage changes by 25 volts every 5 centimeters. 25 volts, 25 volts. Every 5 centimeters, it drops another 25 volts. So the field is 25 volts per 5 centimeters, which is 5 volts per centimeter. Every centimeter I go, it changes by 5 volts. And it's constant. I could have asked for the field at point B over here. It doesn't matter. The field is the same. It's 5 volts per centimeter, which is 500 volts per meter. That's the answer to part A. Part B, I shoot an alpha particle in. It's going 80,000 meters per second when it hits here. Then it starts to go up the hill. How far does it have to go into the field before it stopped and pushed the other way. It's just like a ball rolling up the hill, a gravitational hill. This is an electric hill. Positive charge is going up the hill, stops, comes back. How far does it have to go before it stopped? That's part B. We can get the kinetic energy of the particle. That's the mass of the alpha particle. That's the speed that's given. We can calculate the kinetic energy, and the field has to take away all of this energy. 2.126 times 10 to the minus 17th joules. An alpha particle that's going 80,000 meters per second has this much energy. It stops. KE final is 0. So delta KE is Q delta V. This is joules per coulomb, and that's coulombs. That's the change in kinetic energy. That's how much energy the field has to take away. And the charge, it's an alpha particle that's missing 2 electrons. So it's 2 times the electronic charge that was given in the problem. Alpha particle has 2 protons on it and 2 neutrons. And there's the voltage difference. So we can calculate what the voltage difference is. It's 66.45 joules per coulomb. 66.45 volts. The field is 5 volts every centimeter. And I have to penetrate it to a depth so I can get up to a voltage difference of 66.45. That looks like, well, 13 centimeters would be 65 volts. So it's a little bit more than 13 centimeters. So the answer is 13.3 centimeters into the field. It will undergo a potential difference of 66.45 joules every coulomb, and it has this many coulombs, so the kinetic energy is going to be this much different. So there's the field, 13.3, 5, 10, it's going to go about right there. Notice that these numbers, the value of these numbers isn't important. This could be 150, 125, 100, 75, 50. What matters is the rate of change. It's just like gravitational potential energy. It doesn't matter where you call potential energy level 0. It's arbitrary. That's problem 3.5 from the book. Do more.